Hello, my name is Matthew Pickett, Systems Engineer for Texas Instruments. And today I would like to look at how to determine the ins and outs of instrumentation amplifiers, starting with the difference between an op-amp and an instrumentation amplifier, going into some of the different architectures, and then ending with some common pitfalls that customers usually run into when they first start using them. So the first question is, what is an instrumentation amplifier?
Essentially, instrumentation amplifiers are operational amplifiers with integrated precision feedback resistors, with the main purpose of conditioning small signals in the presence of large common mode signals or DC potentials. Instrumentation amplifiers are derivative of difference amplifiers, but have high impedance input buffers to eliminate the need for impedance matching in your application. TI's INA prefix covers instrumentation amplifiers such as the popular 3-amp INA, difference amplifiers which use a simple topology of 4 or 5 resistors around an amplifier, as well as current sense amplifiers which aren't shown here but are specific to current monitoring applications. There are also programmable gain amplifiers, or PGA, which have the gain options internal and can be digitally controlled. These all have similar functionality but can vary vastly in characteristics. Because instrumentation amplifiers work well in a noisy environment and only gain up the signal of interest in the presence of large common mode voltages, they are suitable for a wide variety of applications, including test and measurement equipment, as well as performing sensor signal conditioning, current sensing, voltage monitoring, and many more.
And now I would like to talk about the different architectures that are available for instrumentation amplifiers, starting with the difference amplifier. The difference amplifier essentially includes an op-amp plus 4 resistors around it. It's also known as the subtractor because it subtracts the difference between these two voltages here and rejects any common mode voltage. The real benefit of this type of topology is that it has an excellent common mode voltage range. Sometimes, depending on how the resistors are set up, even better than or even higher than the power supplies of the amplifier. The limitation will be the input impedance. As you can see, that's limited by the resistance that you have here. So a lot of applications need a higher input impedance. This may not be the right pick for them. And you also are limited to low fixed gains in this type of topology. The next topology will be the 3-amp instrumentation amplifier. This is maybe one of the more popular ones. The strength of this is essentially that it has high input impedance. What this does is it takes the difference amplifier and adds 2 buffers on each of the inputs. Those buffers have a resistive network around it that allow you to be able to gain up the differential voltage. The real benefits of this, the high input impedance caused by these buffers, as well as the ability to gain it up. The limitation is the common mode voltage range. So now you are restricted to the common mode voltage range of this device, and you have to be careful how you set your inputs to make sure that you're not saturating or going into a nonlinear region of your input amplifiers. The next type of instrumentation amplifier will be the 2-amp INA, and what this is very similar to the 3-amp INA, just with a different architecture. And so the benefits are that you get a lower cost, lower power, and smaller size than the 3-amp IA. However, some of the downside is that you are also limited by the common mode range of your op-amps, and because the input has to go through the amplifier before it gets to this point, it can affect the common mode rejection ratio versus frequency due to some phase delay. A lot of the times I'll get questions of why not build my own instrumentation, or why not build my own difference amplifier? Well, there's a lot that is definitely possible, but there's a lot of things that you have to think about while you go into this design.
The first thing you need to consider is making sure you get precision matched resistors. The common mode rejection is heavily dependent not only on the characteristics of the amplifier, but also on the matching of the resistors R1 to R2 and R3 to R4. If you work through the calculations for common mode rejection in this difference amplifier, you can see that 1% matched discrete resistors will give you a worst case CMRR distribution out to 40 dB. 0.1% improves that, but only to 60 dB. In a lot of precision applications, this low of CMR is just not acceptable. TI matches the resistors in its monolithic difference amplifiers and instrumentation amplifiers by a process called laser trimming, where a laser cuts into the resistors, changing their value and matching them during testing. The next thing you need to consider in a build-your-own diff amp is the placement of the resistors. Thermal variation in PCB trace lengths can affect the value and degrade the matching. Laser trimmed resistors not only are excellent for improving matching, but they also are on the same silicon, so they drift the same, giving them consistent matching over temperature, again improving your precision. TI can trim resistors to within 0.01% relative accuracy, which translates to a worst-case CMR distribution out to 80 dB, with an average greater than 100 dB. Once you add up the cost of the amplifier plus the precision resistors, it is much more efficient to go with a monolithic diff amp, plus you will actually save board space.
I talked about common mode rejection ratio, so I just want to give a high-level overview of exactly what it is. Essentially, it's the ratio of differential mode gain compared to common mode gain. And as you can see from this equation, common mode rejection is directly related to the differential mode gain. In the 3 amp instrumentation amplifier where you're gaining that up, you can see that at low gains, for example unity gain, that can cause poorer common mode rejection. It will be truly dependent on the matching of your output stage or the difference output stage. This is an example of common mode rejection versus frequency and a gain of 1 for your typical amplifiers. As you can see, for your typical 3 amp INA, the common mode is around 100 dB. Some of them get as good as 105 dB. However, you are very much limited by the design of the device. The other point to make on this is that it degrades as you go across frequency. And this has to do with the design of the device and the process attributes that are associated with it. There are devices such as the PGA 281 where we have increased the matching by integrating the resistors and leveraging our process as well as a few design techniques to maximize the CMR. Even in a gain of 1, we're able to get greater than 130 dB. The last thing I'd like to talk about would be a few common pitfalls that customers run into when they start using instrumentation amplifiers. The first will be not providing a path for the bias current to go into. On the input stage of an instrumentation amplifier, what you can have is essentially a transistor. Whether that's bipolar or FET, you can imagine that a bipolar resistor needs current going into its base to be able to operate correctly. If it does not have that, you'll see the voltage flow in the instrumentation amplifier will not be in a linear operating region. So, depending on the application, for example in the bridge, that does not need an input bias current path because it has one already associated with it. However, in this example where you have a microphone, the bias current would not have anywhere to go, so you have to add in a resistive path. Sometimes, depending on the application, you can add one resistor will be sufficient if it's a low impedance application such as a thermal couple, or if it can be higher impedance or if you have long traces. To maintain the precision of the instrumentation amplifier, it's important to have matched resistors on each terminal. The other example would be whether it is AC coupled or if you're going into a transformer. If a transformer, some transformers have a center tap, and if they have a center tap, that provides the bias current path. If they don't, you would want to add in the resistors to make sure that you are maintaining linear operating function. The other common issue that is ran into when using instrumentation amplifiers will be the input common mode range. One has to be sure that the input that they're putting on their device is in the properly functioned, so that way it's not saturating the output. For example, if this is an amplifier, even if the amplifier itself includes the negative rail, but if this is not in a gain, that means that the output will try to go to that same place, and outputs can't swing beyond the negative rail, and you'll be in a nonlinear operating region and won't be getting the maximum performance, or you'll be degrading the performance of your instrumentation amplifier. So the thing to look at will be the input common mode voltage versus output voltage curve that is available in most INA data sheets. What this is it tells you inside this square box where is the safe operating region depending on the factors such as supply, your reference voltage, and then you can tell where your output voltage is compared to where your input common mode range is, and make sure that you're operating inside of this box. The last thing to say would be that the reference pin drive needs to operate from a low impedance source. As you can see from this example, the reference voltage is tied to an impedance, and if you were to tie another impedance to this, you will affect the matching of this resistor, which can obviously degrade your common mode rejection ratio. So making sure that if you're going to do a voltage divider, you buffer that with the low impedance output of an amplifier tied to the reference pin. Now this is important, an example for single supply operation where you're going directly into an ADC and you want to level shift the output. You can't just tie two resistors there. You need to make sure that you're either using a reference, such as the Ref 3225, or a buffered resistor divider. And that is what I have. To summarize, we talked about the difference between operational amplifiers and instrumentation amplifiers, talked about some of the trade-offs with the different topologies, and went into some common pitfalls that we face that we run into for these different devices. I appreciate you taking the time today, and please go to the following links for more information.